Here we go. OCR.ai, creating AI to read documents. So this is an evolution of a talk I've done at a couple of these H2O worlds, and maybe some of you have seen this before, maybe you haven't. There's a little of the old, more of the new this time. So this is a project we've been working on with a collaboration with PwC for quite some time. So this project has taken a couple different shapes across the way, but we started showing some of this at H2O World in London actually last year. So we're going to look at the actual work we do specifically for them, but the goal has always been from that one to H2O World San Francisco in February to now it's become even more concrete where we're going with this to actually expose that for other people. So I think that's a big thing I want to bring to this one that's a little different from the last ones you can find. So pretty quick structure of the talk, pretty quick talk. So the problem challenge to show you what we're actually doing. It's been called Document to Vec, it's OCR.ai, it's a lot of little things all in one. We'll go through the actual document workflow. We actually do this with several different documents, but I'm going to pick one of the most mature ones that we have. And it's a little different than what we've shown in the past, so it's a little different. Show the models and specifically the OCR updates that we have in mind for what OCR.ai may become that we do within that workflow. And then the next steps, and this is where this is a bit more promising than the last couple times I've done this. So we are aiming pretty specifically very recently, but at kind of porting this over, getting something a bit more generic, seeing how this will work on a different problem, so that one that we can expose to everybody, so within Driverless. So the task itself is taking business documents of several different formats, and lifting very specific information. This is a task pretty common now. You actually see ads of it on TV and things, invoices, receipts. There's a multitude of documents that we have to work on, and we've been paying attention to two in particular. So last time we've talked about invoices, pretty common document. You buy things online, you get an invoice, usually order summary, those kind of documents, they all look pretty similar. This can be a little different, but structurally it's got a lot of commonalities. But it's important that with these documents, we are aiming at very specific text. So some people ask, is this just OCR? No, this talk is called OCR.ai. So that's our challenge, is to figure out how it can be just OCR. We use a lot of OCR in here, and we've gotten finally some experience to where we can really improve on that. So I actually talked to some people in February at the San Francisco H2O World, and there's a lot of people out there doing that. I got some really good questions and some things we weren't trying back in February. So we're doing a few of those now, so we have a bit more mature of a pipeline. But you see a document on the left, and this is one page. Often our documents are multiple pages, actually. But it looks pretty standard. You see the heading, it's an invoice in this case. So we see some line items. It's probably going to look a little small on your screen, but that blue box in the middle, that's the main focus area, but there's other information we need as well. So we're looking for on any given document, who sent the document, who it's sent to, so the sender and the recipient, usually the date of the document is an important thing for our task. And then line items and some other key pieces of information. So there's really three workflows we have. Two of them look like this. And we need to produce at the end of the day that our predictions are what's seen on the right. So we need to take all that text and really send out, in this case I pulled out 3. In this actual document we'd have more like about 8 or 9 up here, but an invoice date, invoice number, document subtotal. Clear, legible, formatted, moving it in. So digital, of course it's digital when it comes in, but a lot of our documents, even though a modern PDF has embedded text inside it, so you don't necessarily have to do the OCR bit, but a lot of our documents can be sent through a scanner. It's a phone picture these days a lot. We don't see too many of those, but I know that in some domains where people are looking at receipts, it's very common to scan those on a phone these days with ugly backgrounds that don't play nicely with your current OCR flatbed scanner tools. So there's some of the challenges that come up with this. OCR mistakes can be pretty critical for what we're trying to do. So sometimes we don't get to do fuzzy matching for what we have to do in this actual task where it gets deployed. So we have to be really clear, and some of the OCR issues can plague us there in a little bit. So we'll take a look at some of those. So this is the bank document. It's not an invoice. It looks similar, but this is the pipeline we're using at the moment. So the ones in light blue are things we're working on, and I'll talk about those in a little bit, but PDF all the way on the left, that's our document. So we do a few things right up the top. So this is sort of in parallel. These independent tasks is really what it is. So some of these happen in parallel, most of them happen in series. So we do have, we started with some of, the last talk I did was a lot more about the image processing we did. This one not so much, but we do have a faster RCNN model. that tries to figure out where the table is. And so we have labeled it in the past. We've gone through hundreds of these documents, low thousands, and multiple thousand on the invoices of picking out all those regions I just said, except we've gone back and forth on our labeling strategy. This is something where we try to think what will help the algorithm and what won't hurt it, and sometimes we're wrong. So we'll go back and refine things, tighten up our boxes, make some changes here and there. So the faster RCNN model does try and deliver the pixel area of the table. We found it's about equally effective on these documents as treating it like an NLP problem. And so that's kind of interesting. That's why it's grayed out. So we have one of these models. We worked on that. We aren't using it right now in the pipeline. So things we are using. So we do have a CNN logo classifier as well. So logo is kind of an interesting thing. It's often a really good indicator of who sent you the document. They're going to go stamp that up in the top. And logos have some characteristics of CAPTCHAs, is what I call it sometimes. People will be clever with their logos. They're going to alternate their colors, slant it, things that aren't normal text all the time. Some are plain easy to read, some are not. So we have a specific CNN logo classifier, finds the logo on the document for all the pages, which there could be one, there could be none, there could be some. And then there's specific OCR that goes a little harder than normal Tesseract OCR specific to that logo. So we've trained that one a little differently to try a little harder. And then the main pipeline. So then we OCR the first step. So all the way on the bottom left there, you see it's a full document OCR scan. So really in here, the actual pipeline will go through the PDF. It'll crank out images for each of these and then run a Tesseract scan. So, and I haven't said much about Tesseract yet. So this is a big deal of what we're doing with OCR. So Tesseract is sort of it's the most common OCR engine out there right now. So it's currently maintained by Google. I forget my history, but I don't believe it started there, but they currently maintain it. If you're familiar with Google's own toolkit, it is different. It may use it as a basis, I don't know. But their proprietary model does work a little better than open source Tesseract, but it's very common for people working with Tesseract. I got a lot of people talking to me about it in February. Some people within PwC, other groups have used it. It's a very common place to start. We're still using it for a lot of things, and this talk will show you how we're using it a little bit and what you can do to make it better a little bit. So at first, we're taking all the pages of this document and scanning every single one, scanning with Tesseract goes through. So we're using it in a mode that delivers it you can think of it as pandas data frame that comes back a CSV that tells you the coordinates of we're running it in token mode where you get words as tokens. So it's space delimited, and that can be one thing, sort of a capture with that. Gotcha. It doesn't always put the spaces where you expect them. But that's the best way to start. So you get a lot of your pixel coordinates, how big, how wide, where it starts, where the start of the box is, and then the text that it feels. You also get a confidence as well, and it's reasonably calibrated. So you can use that for some information as well. So the whole document we have at that point, and we treat these like entire documents because the information we want to find could be on page 1, it could be on page 3, it could be on page 7. There could be header stuff. We don't know what's in there just yet. So we want to look at the whole document. So some of the OCR normalization that we put in at this point is just simple stuff of just making it all look like one document so that the top values is just how they record your pixel. You can think of it the Y value of an entire, say, 17-page document. So usually, and it's DPI, we usually run it at 300 DPI. You get about 3,500 pixels. And then that just continues on to 20,000 or so forth. Talking a little ahead of where we're really at. But so the OCR and standardization. So the standardization is a little bit of that. It's trying to just do things so we can work with that document because we're going to move into NLP world a little bit, or maybe even text mining, that kind of stuff. On that path. So it's no longer the image models. We're using the OCR because on our training data, the OCR actually made very few mistakes, and the mistakes it made were not critical. It looked like we could work around them. We've since stumbled into data sources where we're being a bit more challenged on that, so we're having to use some of these tools even better. A lot of focus on trying to fix these results, so that's what we'll talk about a little bit. So the OCR, we get a big giant CSV of all of our words that are in the document. Words or anything that's space delimited. So with us, we're dealing with a lot of numbers, a lot of things that don't have sentences. That's a big difference between normal NLP and what we're doing. These documents have layout and they have structure, tables, things like that, and implicit tables sometimes. So it's a bit more like short fragments than big sentences. So the first step is the line classifier where we take all the documents, the text, and put it back together like a single line. So you're reading it almost like paragraph form, which there's a way you can even run it exactly like that, but it doesn't return all the metadata that we need to work it out. So we just work that backwards and put it back in. And this is where we go after the segmentation mode. So that faster RCNN table classifier that's up in the top is doing the similar work to these line classifiers. So looking at the entire document, and these are classifiers that just say, what am I of the things that we want. So a lot of the stuff out there is stuff we don't want. We don't care about it. It's very little that we care about, to be honest. But these job is to look at the entire line and see what's in the line. And we send that over, and then we refine what's in the line with the term classifier. Got more slides on these too. And then we have some of the tools of actually fixing up the OCR. So it then goes in this chain reaction of things we can do to improve what we're looking at. So we parse it as a table. When we can get it in that format, we start to learn things about where the OCR scan may have gone badly, and we can rescan specific segments of that, and I'll talk more about that. But the same after that, alignment and validation. So we have to align a lot of our line items. They may be just straight left to right. They may all be in the same line. That's fine. That's great. Sometimes they're not. They're off by 2, 3, 4 lines. They may be disconnected by quite a bit. And for our job, we have to deliver the answer of this line item and all the components that go with it. And so actually associating those correctly is somewhat of a challenge sometimes. And here, something we're working on is targeted OCR rescans as a reaction to that. At the end of the day, we produce 2 things, text predictions and box predictions. So the actual text that we found, and we need to show people where we found it so we can highlight those, and Tesseract works really well for that. So here's an example of our logo classifier. So this was up at the top. So one of the first things we run is a logo classifier. I've got a couple of them here. We have NatWest up in the top. So the logo classifier usually pretty high, so 99.6% clears the logo. On the bottom, we can kind of see a few of these examples of some of the banks we've looked at. Interestingly, the logo classifier was trained on invoices, and we usually test it on banks, and it actually works really well. It's just really, and that's why the logo classifier is kind of this widget you can put in probably any document. You're really looking for the document author, and an invoice, it's not a bank, but for this bank documents we're talking about now, they are banks. So these are 2 banks up in the top. Logo classifier does a good job, 99.6, 96.8% finding that. And then when we turn into text, I've shown, there's a 4th one I almost had, that occasionally what we see is 1 extra character on the side. So it's turning some of that logo. It will sometimes make that into something. We can pretty quickly trim that out. So the logo classifier is a pretty easy way of figuring out who the document author is, which is important. It's one of the 6 things we're looking for, and one of the 8 or 9 on the other document. The logo classifier is independent of these H2O3 GBMs. So this is where I was talking about we're going to look at the entire line. The reason for looking at the entire line first and then splitting it out is that the line classifiers can see multiple clues of the same thing. For something like a bank or the company, that's not too helpful, maybe, it still is because you're space delimited, I suppose. You can see multiple characters, or multiple, tokens at the same time. So we often string many of them together, 6 or 7 might form a company name with all of its limiteds and corporations. Particularly here, the table classifier is the main thing we need out of this. So the tables are the featured piece of this. And so the tables, we can look at the 3 things we want, which are, in this case, it's a bank account, a balance, and a currency. We have, in other documents, it's different things. So the same idea in invoices. Invoices are a little harder, actually, for this. Just the format really changes. Some people use paragraph form to actually word out, what they want. We still have to get those. So it's not, we call it a table, but it's a loose definition of a table. When you look at real documents, I have an example of an Apple invoice, actually, and oddly, it's a table, you can see it, but you can imagine how an algorithm would stumble on this. So these attack all 3 of things we're looking for, and so it really helps to look at them not individually, but all as a unit. So we often see this doing a pretty good job of withholding things that our later models would have classified incorrectly. So it actually helps us a lot focus on the right table. The right table tends to be up towards the top. We often get things like loans that we're not concerned about in this particular use case. And so these algorithms are trained that way to use all the Tesseract clues, to use some pretty simple regexes. And that's the sort of stuff we'll have to see how much mileage we can get out of that with other applications through receipts. So receipts is where we're headed, to try and show how this can work for other people. And I think we'll be able to get some use out of some of the things we've done here, at least these experiences, and we'll be able to bake that into driverless. And so So the results of these H2O3 GBMs, so this is H2O3, just pretty simple models, pretty simple features. The line classifier, the table classifier, sorry, is about 97, 98% accurate at this point. And so we're, as the notes kind of say, we're concerned about false negatives. So if it does not select something, I've weaved together an A-B sort of model here. So my A model is going to send the results into the B. If A is wrong, that's okay if it's sending too much stuff. We have a hope of kind of cleaning that up. If it leaves one out, then we're in trouble. So these are sort of cautioned with a lower threshold than we might need, but they still do a pretty good job of not sending up too much stuff, too much extra. And driverless cleans a lot of that extra up. That's what we see most of the time. So here we actually get real driverless. These are NLP models, and so we have 3 of them. You see those 3. We actually have 4 now. There's 2 variants of the balance model. So we have independent models going after each of the pieces of that table, and you can see they're clearly named on the right, the account, the currency, the balance. Some of the features are listed over there. These change. I think I've got a screenshot of one of the older models that we have, but we typically see all 3 variants of what driverless does for NLP models. So we see character level CNNs, so convolutional neural nets, not image-based, but this is text-based, obviously. Word-level CNNs, and as well the bidirectional GRUs. So those are the 3 main things that have been in driverless for quite some time. We're using usually all of these between the models that we see across the different documents. This one may have all 3, I'm not quite sure at the moment. So the driverless AI model's job, like I said, is to kind of see it on the right side. In the middle is the text, and so it's just one word at a time. So it has been sent over the results of what we're looking at, the results of that table, and now its job is to throw out the stuff we don't care about and just isolate the specific things we care about. And a lot of these tables will have extra things in there, an interest rate. If we're doing invoices or something, you may not need a quantity, the invoice price, the tax, all those kind of things. You may want them, you may not. So there's a lot of extra stuff. Most what driverless is doing is shutting things out here, but it also does get a little extra stuff coming in from the classifier, from the table recognizer, the table models. And there's also a distance thing here. So we've learned that, so we're using the results of the table classifier to tell driverless how far everything is from the start of a table. And that helps us actually go up from where we think the table is to go start to read some of the header content. We've had differing results on trying to do that, but it helps us isolate features of what's above it. So some of these tables can stretch on for a while, and the actual clues, the best clues you have of what you're looking at is actually above the content you're trying to find. So there's two things kind of going on here, and we try to use both of those in with these models, and we can use those selectively. The models are highly accurate, as you notice from here. I didn't really even address that, but these are almost silly accurate. 100% on the test set on 2 of these, 99.3 on the other one. It's really unbalanced. So a lot of the stuff we get in here we don't care about. So we do have a lot of tokens that we don't care about, and that goes all the way from the line classifiers. We're looking at sometimes it's a one-page document, but most often it's multi-page documents. We usually get in the order of maybe 1,000 plus tokens in here, and we usually only care about a small handful of them. We do have, so what I've just shown you here is 3 different binomial models. The account job has one job to do, the currency model has one job to do, the balance model has one job to do. We've also experimented with pipelines where we have multinomial models in there. And when you have 3, that's not a big deal to maybe have 3 models all chained together. Fortunately, right now they're fast. We use driverless since 1.6, and we didn't have mojos, and we paid a really big price and speed for that. So that's one really nice thing. The driverless models since 1.7.1 have had mojos. We still have one that we have to work out some of the settings on even with 1.8, but driverless does a good job getting out fast mojos finally. That was really a struggle. We would test ourselves on a few hundred documents, and it was taking us a minute and a half to load these. So if that's you, if you're going through these Python, using the pipeline, the wheel file, go for a mojo. If you can orchestrate that, they feel like they're super fast to us because we've spent so much time working without those. So with the mojos, you don't have to have such a big model. It's not that big a deal to have 3 of these models. So before it was about, again, a minute and a half for each one, but we needed it for the accuracy. But now with the mojos, we could probably do multiple. One of the other documents, though, for contrast, the invoices have about 8 or 9 classes in there. So we're using a multinomial. One of the biggest reasons to think of how that works is that Tesseract is spacing its tokens in a certain way. And at the very bottom, you see an example, GBP 0.00. For me, that's a balance, 0.00, and it's a currency, GBP. and it's been smashed together because there's no space there. Tesseract doesn't read the space. Sometimes the document doesn't have a space. So it's actually dually both things at both times. So it's really like a multi-output problem, not just multinomial. Right now, we don't handle those. It's not common. Well, we don't handle those. I'll just keep it at that, at driverless. So in that case, what we had to do in the other one for the multinomial model is create a special class or experiment with having a special class that can actually do both of these. And so that's kind of a catch. So with the OCR, this is one of the common problems we experience. Is how we're fighting sometimes these spaces and what they're doing to our predictions and how you can potentially need two things in once. So some of the other specifics that we have are alignment and resolving multiple references. To keep this one quick, we have to align the line item. I mentioned that a little bit. And so on the bottom right, you start to see something where it's not that hard. You can imagine as a human, you can read this pretty well. But we have to keep that left column and actually the second to right column and the third all the way right on the right all together. So because those are all three parts of one unit. And in a lot of documents, it seems obvious, especially to a human. But we can lose things in many different ways, as we've discovered. So the models themselves are actually all reasonably highly accurate. But putting it all together, all these independent models, when you break up your workflow like this, you invite errors, and we experience that quite a bit. So something as simple as aligning, and this is a better example of one here. So I've highlighted on the right what we want. Those yellow boxes are the line items. This is an Apple invoice, and we have this. So sometimes it's clear. You can see on the right, they're calling out one value, but sometimes it's not clear if that value belongs to the thing below it or above it. So these are fairly tricky for us to sort of resolve. And so we have special code that starts to work on these known sets. And that's really different from problem to problem to problem, unfortunately. So for this one, we know that we almost always need all three pieces of information, but there are some special conditions where we may be missing one completely. When we move to invoices, it's very common for someone of 8 things that we want, or out of the line items, I think there's about 6. It's very common to only have 3 of those or 2, so there's only so many checks you can put in. We have a lot of code that's spent trying to fix these, where we find things intermingled, some of our predictions. And then that kind of bled into this one, custom validation. So another reason this can happen, so the driverless models, since we're dealing, if you think of multiple line items, we're dealing with almost a weird case of multi-output. So we have 3 occurrences, 3 balances, 3 accounts. And what that means in modeling terms, and the binomial models we have to use a threshold. We can't just pick our best one. In the header content, we can kind of get away with that a little bit. We do expect a bank in there somewhere. Occasionally we may not have one, but we almost always do. So for here, so we have thresholds that are all sitting around 0.5, but it just turns out some of those squeeze just below that threshold, and they'll be clearly the best choice. So by the time we've isolated these lines, we know, again, where to look a little more for these. So we can recover some of the driverless balance predictions that it may have missed. It may have just 38% instead of 45 is our threshold. So these custom validations are things that we know with this problem we've been able to set up. So that'll be difficult. We'll see where that goes in the receipt world, how much mileage we can get out of that kind of concept. But it's very common with invoices and as well with these bank documents. So specifically now to some of the OCR tactics we've put in. So these are still somewhat immature, but we're getting a lot of use with some of our new data sets that have more challenging OCRs. This document is one I pulled from the Tesseract page, but I'll show a couple of real ones. So again, like I said, the original OCR rescans on the whole page, or really all the pages, and we've weaved that all together. But each individual page is done separately. So we've looked at a page, and the Tesseract is very picky. They have a lot of image processing that happens underneath the hood. And so one of their typical tips is to try and binarize your data as well as you can. So take a hold of that with image tools. We're getting a similar reaction in a different way. You can sort of restrict the color space of what you're trying to scan with Tesseract if you isolate just a small portion of it. So rather than look at the entire page, look at everything. And at certain modes you run it will run every single character separately. If we tried some of these tactics up front, it would take us forever. So what happens here is, so by the time we've whittled down, I keep saying like there's a lot of extra stuff. We're really looking for a small section of data. So after these models have all run, some of them perhaps with OCR mistakes, but we've isolated pretty well what we're looking for. So we have a lot of time to be able to rescan through OCR. So the OCR, there's a lot of different, you can think of them as hyperparameters. If you want to take it to a machine learning world, that's really what the Tesseract parameters are. And so the binarization is one of the things that we can do. By selecting, we sort of get a free pass on that one, but there's a lot of other options you can use. So different segmentation modes, there's several of those that you can use. Whitelist, blacklist. So whitelist, if we know we're looking for a balance, we might want to feed it, get rid of the alpha characters and keep the numerics actually, and special characters. Because a very common mistake I have listed here, so an O versus a 0, Tesseract tends to push things towards the language that it was trained on. So zeros in our world often turned up as O's, but that can cause problems when we're trying to do quite a lot of stuff. The pipes come in, so I haven't talked about this just yet, but pipes are a really nice way that a document author will tell the person they're trying to give that document to where the table is and nicely lay everything out. That's great. It actually makes Tesseract worse. So Tesseract sees those pipes and makes it into a language model, sentence left to right. So we see a lot of pipes in our data set. Next slide talks about something we've looked at to overcome some of that. We just kind of deal with it at the moment, but we looked into some specific ways of getting rid of some of these. S5, and I don't even know what to call it, but the character at the very end, the paragraph sign I think is usually what it's called. Those are examples of whitelist, blacklist we don't use so much that I know of, but, or even separately trained models. And so that's where we'll certainly look towards as the receipt goes in. And so we've gotten some other people involved in the project that may take a kind of a, look at augmenting of what Tesseract does. So either a separate Tesseract, but really you can retrain Tesseract on your own documents. And we've tried that. We don't want to do that. It was worse if we did it across the whole document. That's probably for me. But again, if you're in targeted mode, if you're really specific of what you want, then you have time to try. It's not a big deal to try 8, 10, 12, 20 things. So this is almost like trying AutoML on specific pieces. You can really try lots of different hyperparameters. You got to have some sense of what comes back. You can use the Tesseract confidence, or if in these cases where we have sometimes O's and zeros, we know it's very likely a 0. Some of the other stuff we've looked at, de-skewing things. This is also on the Tesseract best practices. We saw a few documents. If the document comes in skewed, and it doesn't take much, like I was playing around with some of these, 1 degree, 2 degrees is all it really takes on some of these to do that. But there's easy image processing tools to de-skew things. On the right side, contour recognition, the idea is you pick up lines and you remove them. So turn black into white. It actually helps Tesseract a little bit. Actually, probably won't show that one. It takes about 30 seconds to run one of these pipelines. I know I'm already out of time, but just to prove that this stuff actually does something, I'll do that and show you what it does. Some of the stumbles we've had in the past, I'm not going to talk about this. Next steps, that's really the crux of this one. So our goal now is to, with H2O, so we have sort of a separate team ramping up that's going to look at trying to take some of the best practices we've had and take a fresh look at somewhere where we have more data. We've struggled to have open source data on some of this, so that's the one thing that working with PwC, they've got a lot of these documents that we can use, and so our training volumes have increased over time. That was kind of the spirit of the last couple talks. But with receipts, there's a lot of receipts out there. So we're gonna take our hand at trying to set up receipts and look at custom OCR for that. Putting that in Driverless has already worked to sort of make that happen. So we hope next time we can do one of these talks, that'll be a reality that we can actually show you what Driverless looks in there. But this is absolutely active work that we're working on, and we're hoping to make it accessible to everybody else. And so hopefully this guy's done. Yeah, there we go. 43 seconds, and just take my word for it. At the bottom, it says all ones across the board, and it'll come up with something that looks about like this. So we found our logo up top, and this is our augmentation. So whoops, sorry. Well, maybe we'll really just leave it at that because I'm over time anyway. So, but we box everything up as part of our debugging process. So I sit there staring at red boxes on all of our documents, and the output, we just kind of work through the text of that, and we have a matching process. It's integral for this, not so much for the receipts. So with that, I think I'll close. Thank you very much.